Welcome to AI Paper Sop. Today we are doing a deep dive into the paper EvoArena Tracking Memory Evolution for Robust LLM Agents in Dynamic Environments by EvoMem and a team of researchers.
Right, from NUS, MIT, and a few other places.
And if you are building autonomous agents, the core insight you need to hear straight away is that your benchmarks are lying to you.
They really are. I mean, they assume a static environment, but real-world deployments are incredibly dynamic and constantly evolving.
Exactly. So this paper introduces EvoArena, which is a new benchmark for evaluating agents in persistently changing environments, alongside a Git-Like patch memory system called EvoMem.
Because they found that top models suffer from this thing called state collapse when things change.
Right. They fail spectacularly at multi-step evolutionary chains, but by recording exactly why a memory changed rather than just overwriting it, EvoMem boosts reliability across the board.
It really is a critical wake-up call for anyone putting agents into production right now. We have been optimizing for a target that simply does not exist outside the lab.
Yeah, we are building systems that can solve a frozen snapshot of a problem brilliantly.
Exactly. But the moment an underlying API updates or a permission changes or a user's preference shifts over, say, a 3-month timeline, the agent just completely breaks down. We're building glass cannons.
Let's really pull that apart, because existing leaderboards for things like WebArena or SWE Bench, I mean, they show the numbers going up every single month.
Oh, constantly going up, yeah.
Right, and we look at those charts and think our agents are becoming these incredibly capable software engineers or web navigators. But you're saying that gives us a false sense of security because the testing environment is basically sealed in amber.
The illusion of the static snapshot is profound. When you test an agent on a standard benchmark, the interface it interacts with, the rules of the system, the task distribution, it's all entirely fixed.
The success criteria doesn't change.
Right. Once the benchmark is compiled, the world just stops moving. But think about actual deployment. A reliable agent running your infrastructure has to know what changed from yesterday.
Yep.
It has to know what rules from last week still hold and how to act under the current version of a living system.
Which the authors call persistent environment evolution, right?
Exactly. The idea that the overarching setting remains the same, but the operational realities inside it change across versions.
I want to make sure I'm distinguishing this from just giving an agent a brand new task. Like, we aren't talking about asking an agent to write a Python script on Monday and then asking it to book a flight on Tuesday.
No, completely different.
We're talking about asking it to maintain that same Python script, but the dependencies underneath it keep updating.
That distinction is paramount. The overarching goal might be exactly the same, maintain this microservice. But an API dependency upgrades its authentication method.
Right.
Or workflow permission in AWS shifts. Or a human manager decides they want error logs formatted in JSON instead of plain text.
And when an agent faces these persistent changes over time, they hit that massive failure mode you mentioned, state collapse.
They collapse, yeah.
That implies something structural is falling apart inside the agent's reasoning. What is actually collapsing there?
The agent's memory architecture. When you look at how most current agent memory systems are built, whether they are using episodic stores or just shoving observations into standard vector databases, they maintain a single latest state.
So it's essentially an overarching CR-UD application where updates just overwrite previous entries.
Exactly. When a system rule updates, the memory system retrieves the old rule, realizes it's outdated, and just overwrites it with the new rule.
It honestly sounds like a junior developer who just constantly force pushes over the main branch.
That is exactly what it's like.
Like, they encounter a bug, they write a fix, and they just overwrite the entire file without leaving a commit history.
And if you don't know why a piece of code is there, deleting it or overwriting it usually breaks 3 other things you weren't even thinking about.
Right. So are current LLM agents essentially force pushing their own memory?
That is the perfect analogy for the mechanism here. And, well, it works completely fine if the new information perfectly and safely supersedes the old information.
But real life is messy.
Right. What if a workflow permission update overrides a rule that actually still applies to a different legacy part of your organization?
Right. Or what if the system has an outage and rolls back to an older release?
Exactly. The agent has lost the context. It force-pushed over its own reasoning for why it acted that way in the past, and now it has no idea how to navigate the reversion.
So force-pushing memory is bad because it destroys context. But to prove this is actually happening, the researchers couldn't just run agents through a static maze.
No, they had to build a maze that changes its layout while the agent is still running inside it.
Which brings us to how they constructed the EvoArena benchmark itself.
And building a dynamic benchmark is incredibly difficult because you have to measure sustained reliability, not just a single moment of brilliance.
Right.
So they tackled this by scoring the agents on two distinct metrics: step-level accuracy and chain-level accuracy.
Step level would just be solving the individual task right in front of the agent at that exact moment, right? Like, can you adapt to this one specific change?
Yeah, that tests local adaptation. But chain-level accuracy is the brutal one. To get a single point for chain-level accuracy, the agent must solve the full sequence of linked tasks across the entire evolution chain without failing a single time.
Which makes total sense for production environments.
Right.
Because if you pay for an AI software engineer and it successfully ships a feature on Monday, patches a bug on Tuesday, and optimizes a database on Wednesday.
But then completely corrupts your production environment on Thursday because of a silent infrastructure update.
The whole workflow is ruined. You'd fire that AI immediately.
Exactly the stakes we're dealing with. To test this, EvoArena uses 3 different evolutionary domains, starting with terminal bench Evo.
Okay, so that tests executable workflows in an evolving shell environment.
Right, and the baseline task is deceptively simple. Just deploy a file called hello.html to port 8080.
So the terminal is a relatively isolated environment. It's a standard 101 tutorial task. How does the maze shift?
The environment evolves across 4 versions. In version 1, the agent tries to deploy via a post-receive Git hook, but the first push intentionally fails due to a simulated network hiccup.
Ah, so the agent has to learn to retry?
Exactly. Then we move to version 2. The deploy directory suddenly shifts from the default to /var/www/new.
Okay.
In version 3, the environment evolves again. The web root is secured, so the deployment now requires www data group permissions.
Oh, wow.
And finally, in version 4, the server configuration changes to reject pushes to the master branch entirely. It only allows pushes to main.
Oh, that is devious engineering.
Isn't it?
Because if the agent just updates its memory to say always push to master to deploy, it sails through the first 3 versions and then crashes on version 4.
Right.
But if it just remembers always deploy to /var/www/html, it fails way back on version 2. It literally has to track the delta of the environment.
It has to track the delta, and more importantly, it has to understand which constraints are additive and which are substitutive.
Right, because the terminal environment is relatively contained. But what happens when the agent's actions have compounding long-term consequences, like in a shared code base?
Yeah, that leads into their second domain, which is software engineering, SWE chain Evo.
And this tests chronological code base commits using real-world open-source repositories, right?
Exactly. The paper highlights an incredibly telling example using the AOTTP repository.
Okay.
The agent is tasked with implementing a sequence of milestones over time.
Okay.
First, it has to harden deserialization to reject malicious payloads. Several commits later, it has to block header injection vulnerability.
Sure, standard security stuff.
Later, it encounters an issue where it needs to preserve empty values during parsing. And finally, much later in the chain, it has to fix a bug where the local time is calculated incorrectly during daylight saving time transitions.
And because it's a chain, it has to implement that daylight saving time fix without breaking the header injection protection it built 20 commits ago.
This is where we see the introduction of pass-to-pass regression tests in the evaluation.
Oh, okay.
The agent has to implement the new feature, and it has to pass the fail-to-pass test for that specific new requirement. But crucially, it also has to pass all the historical pass-to-pass tests to prove it didn't break older milestones.
That is a high bar.
It is. If you look at the architecture of these agents, when they hit that parsing issue with empty values, their episodic memory might realize that the previous header injection block is getting in the way of parsing the empty values.
So the agent just deletes the security block because it force-pushed its memory.
Exactly.
It thinks, well, this block of code is stopping my current task. I'll just remove it entirely, forgetting that the block of code was put there to stop a critical security vulnerability.
It forgets the rationale for the code's existence. And the success rates on this are staggering. Base agents averaged only 10.6% on the SWE chain Evo chain level accuracy.
10.6%. That means nearly 90% of the time, the agent breaks the code base or fails to adapt over a sequence of just a few related commits.
Right. It's not a tool you can use in a professional setting.
That's just a fundamental architectural failure.
It really is.
Well, if legacy code is messy to track, human preferences are an absolute nightmare. which leads into the third area they tested, focusing on social intelligence.
Domain 3 is Persona Mem Evo. They give the agent over 170,000 tokens of chat history per persona.
That is massive context.
It is, and the agent has to track temporal preference trajectories. These are a great example of a user whose relationship with an activity changes over time.
Okay, how so?
Initially, the user talks extensively about preferring intense hiking. Later in the 170,000 token chat history, they get injured, and they explicitly state they are avoiding hiking. Even later, they recover, but now they mention preferring light trail walks instead of intense hikes. Then, the agent gets queried on what activity to recommend for a Saturday afternoon.
I have to push back on this testing methodology a bit, because humans contradict themselves constantly.
Oh, for sure.
Like, I might tell an AI I'm going on a strict diet, and then my chat history is full of late-night pizza delivery requests. How does the benchmark know the agent actually tracked the temporal memory of the injury and recovery and isn't just hallucinating the right answer based on some generic stereotype of an outdoorsy person?
It's a vital methodological question, and the researchers actually anticipated the hallucination problem. They implemented a very strict, dual-blind filtering process for the evaluation questions.
Oh, okay. How does that work?
First, a question is completely rejected from the benchmark if an LLM can answer it correctly, using just the basic persona profile. So, no generic stereotypes allowed.
Nice.
Second, they reject the question if it can be guessed with no context at all.
So there's absolutely no way to shortcut the reasoning. The agent literally has to ingest those 170,000 tokens, map out the chronological timeline, pinpoint the injury, pinpoint the recovery, and synthesize the current preference.
And they make it even harder by deliberately building distractors into the multiple-choice answers that correspond to outdated preference states.
Ah, to trap them.
Right. If the agent suffers from state collapse, queries its vector database for hiking, and just grabs the first highly embedded result from before the injury, it will confidently choose the wrong answer and fail the chain.
Okay, so the problem is undeniable. The force-push memory architecture fails across shell environments, software engineering, and human social tracking. This brings us to the paper's proposed solution, EvoMem.
Yes, EvoMem.
They call it a Git-Like memory paradigm. If we know the agent is destroying its context when it updates, EvoMem must be stepping in to save the delta between the old memory and the new one.
It saves the delta, but if it just saved the data difference, we'd still have the context problem. EvoMem doesn't replace the agent's base memory updater. It monitors the transition.
Okay, how exactly?
Yeah. Whenever it detects a non-additive update, meaning a memory is being actively revised, overwritten, or reinterpreted, it intercepts that process and forces the model to generate a structured patch.
So it's not just logging the change, it's forcing the LLM to write a commit message. What exactly goes into that structured patch to make it useful later?
It captures the before state, which is C pre, and the after state, C post. But the magic is the reasoning layer.
The rationale.
Exactly. It forces the LLM to generate a rationale, RAT, literally making the model write down why it decided to overwrite that memory. It also records ET, the specific triggering evidence from the context that proved the change was necessary.
Oh, that's smart.
And finally, it generates ZT, the tiny semantic summary of the entire change, so it could be easily searched later.
Wow, it's literally a database write-ahead log. Or, to stick with our developer analogy, it's Git's Git blame feature built directly into the agent's cognitive architecture. We are forcing the AI to explain why it changed its mind and logging that explanation.
And that logged explanation becomes actionable at inference time. When the agent gets a new task, it doesn't just retrieve the latest facts from its base memory.
What does it do?
It takes the current query, embeds it, and searches against those semantic summaries we just talked about. It retrieves the relevant patch history and concatenates them together in the prompt.
So the agent literally sees its own evolution trace. Like, here's the current rule, and here is exactly when and why we changed it from the old rule.
Exactly.
Wait, if we are pulling historical patches, rationales, and the before and after states into the prompts every time the agent takes an action, doesn't this massively bloat the context window?
It sounds like it would, yeah.
Because we can't just shove the entire Git blame history of a code base into a prompt every time we ask an agent to write a line of code.
That's where the semantic summary comes in. EvoMem uses patch-augmented retrieval. It does not dump the entire history into the prompt.
Oh, I see.
It calculates the semantic overlap between the current query and the patch summaries, and only retrieves the top or most relevant patches.
So if the query is about a completely stable part of the environment that hasn't changed, no patches are retrieved at all.
Exactly. It only pulls the history when the current task collides with the known revision.
So it's a highly targeted, surgically retrieved Git blame. Let's look at the actual performance impact. We know the baseline models crashed and burned at 10.6% on the software engineering chain. What happens to the success rate when EvoMem is running?
The recovery is remarkable. On the EvoArena benchmark, EvoMem boosts chain-level accuracy by an average of 3.7% across various models.
That's a solid jump for a dynamic test.
It is, but what is arguably more impressive is that it doesn't just help on this specific dynamic benchmark. They tested it on standard static benchmarks as well.
Really?
Yeah, it boosted GAIA accuracy by 6.1% and Locomo, which tests very long-term conversational memory, by 4.8%.
A 6% jump on a highly competitive benchmark like GAIA just by forcing the agent to track its own memory updates, that's huge. And I love when papers provide mechanistic proof instead of just black box metrics. How do we know the agent is actually reading those patches and not just benefiting from a slightly more verbose prompt?
The researchers actually did a deep dive into the underlying mechanics. In the terminal bench domain, they measured a phenomenon called patch uptake.
Patch uptake, okay.
They tracked whether the agent actually took the specific terms, flags, or directories from the retrieved patch and put them directly into its executed shell command. When patch uptake occurs, accuracy jumps by 8.3%.
So it's literally reading its own generated commit message and realizing, right, we need to use the www data group permission now because we secured the web root 3 steps ago.
Exactly. And in SW chain, the software engineering domain, EvoMem, significantly drops those pass-to-pass regression failures we talked about earlier.
The ones where they delete the security patches.
Right. For instance, when running the Kimi K2.6 model, regression failures dropped from 7.14% down to 3.3%.
Wow, cut in half.
The agent stops breaking old code because the retrieved patch reminds it why the old code was written that way in the first place.
And in the social intelligence domain, tracking the hiker's injured ankle. Does the rationale help there?
It does. They measured row-level capture, which evaluates whether the agent preserves the complete set of evidence needed to answer complex temporal trajectory questions.
And it did.
EvoMem boosted row-level capture significantly. The agent successfully held on to the full timeline of liked hiking, got hurt, likes walking, rather than just overriding its vector database with a flat likes walking factoid.
The performance gains are undeniable, and the mechanisms make total logical sense. But as engineers, we have to talk about the cost.
Oh, always.
Because in the paper, there is a fascinating token consumption analysis. You mentioned earlier that the PersonaMem histories are 170,000 tokens long. How computationally expensive is this patch-augmented retrieval system?
The token breakdown is one of the most revealing parts of the study, actually, because it highlights the efficiency-accuracy trade-off. In the terminal bench evaluation, the GPT 5.5 model achieved the highest overall accuracy, hitting 62.8%.
Okay, solid score.
But to get that score, it consumed a massive 505 million tokens over the evaluation window.
500 million tokens.
Yeah, it's wild.
If an agent is using 500 million tokens just to navigate a changing terminal workflow, we have to ask a serious architectural question. Like, is the model actually reasoning better? Or is it just brute forcing a massive context window until it stumbles upon the right shell command?
That is the exact tension the authors highlight.
Because you cannot ship a 500 million token prompt loop to production. The API bill would bankrupt a startup before lunch.
Completely. Yeah. Higher token usage does not reliably translate into better reasoning. Sometimes it just exposes wildly inefficient search mechanics. When you look at models like Gemini 3.1 Pro and GLM 5.1 on that same terminal benchmark, they achieved very strong accuracy, 53.8% and 51.8% respectively.
Okay, so slightly lower, but still very good.
But they operated at around 80 million tokens. They were way below the average token usage while maintaining top-tier performance.
So those models were actually reasoning efficiently through the targeted patches rather than just churning through an endless context window hoping the answer fell out.
Exactly. And we see the same pattern in PersonaMem. The Gemma 431 Beat model achieved the highest accuracy on the complex social intelligence tracking, but it used fewer tokens than the cross-model average.
That's fascinating. It completely invalidates the current industry trend that throwing a massive context window at a problem is an acceptable substitute for an intelligent memory architecture.
It really does.
Which brings us to the ultimate question for the people listening right now. If you are an ML engineer building an agentic workflow for your company, maybe you're building a coding assistant or a long-term customer support agent, what should you fundamentally change about your architecture today based on this research?
The core takeaway is that if you are building agents for long-term deployment, your memory system cannot just be a simple vector database of the latest facts.
Right, the force push problem.
Exactly. It is no longer enough to just retrieve the most recent observation. Your memory architecture must be an auditable, versioned history of grounded updates. You need the agent to have access to the diffs and the rationales for those diffs.
You need get blame for your agent's brain.
Perfect way to put it.
Because real-world deployment is the ultimate chain-level benchmark. Your agent can successfully navigate your code base on Monday and Tuesday, but if the environment shifts on Wednesday and your agent has force pushed over its own reasoning, one broken step ruins the entire workflow.
Yeah.
It has to know not just what the state of the world is, but exactly how and why the world got to that state.
When you integrate that historical rationale into the prompt, the agent stops acting like an amnesiac, reacting to the present moment, and starts acting like a system administrator who actually read the documentation.
Which leaves us with a massive engineering dilemma to think about as we wrap up. EvoMem proves that agents absolutely need a history of their own memory updates to function securely in dynamic environments.
Definitely.
But as these real-world deployments run for months or years, the append-only patch history is going to scale. And how do we prevent this versioned history from becoming an infinitely scaling context window nightmare?
Right, because it just keeps growing.
Exactly. Vector similarity search helps, but at some point, these agents are going to need to learn how to forget, but they have to learn how to forget safely without causing state collapse all over again.
Deciding what is safe to permanently delete from an agent's memory trace is going to be the next great frontier for this kind of architecture.
Something to mull over while you're designing your next retrieval system. Thank you for joining us on this breakdown. Stay curious, keep building, and we will catch you next time on AI Paper Slop.